That's a great question that we'll talk about another time, but not right now. Okay? Lesson 3, orbital or cosmic potential energy, or really, how do we calculate how much rocket fuel we need to put something in orbit? Well, we're going to calculate how much energy we need to put something in orbit in joules, and then you would know how many joules per liter of whatever rocket fuel that you're using. This is the start of figuring that out. We're going to ignore air resistance. You're already going to see, just even in ignoring air resistance, we're doing a lot of calculations. It's really impressive that scientists, rocket scientists, are able to so accurately put objects in orbit. So here's my question. Why can't we use potential energy equals mgh in outer space? There's gravity in outer space. We've already talked about that. Remember, gravity reaches all the way out to the moon. Believe me, it reaches to our satellites. Yeah? Sorry? No. Here's the problem. Little g is changing. It's not that there's no gravity, but it's weaker gravity. And if you had said that, my little math nerd heart would have gone ding, ding, ding. Yeah. So what we need to do is come up with a version of cosmic potential energy. And spoiler alert, it better have an R for radius in it somewhere that takes into account as we go further out, the gravitational field gets weaker. So we're going to have to go back to one of our definitions of work. The area under a force versus distance graph is work. I'm going to be really specific though. So can you label the y-axis with force in newtons and the x-axis with distance in meters? And then draw a line that starts out kind of low and gets high, because that's our changing force. Starts out small and gets bigger and bigger and bigger. And then somewhere, I don't know, right about here, put a point, call it lowercase a. Put a point right here, call it lowercase b. And then we're going to draw in this area. We're not going to bother calculating it, but we want to talk about it. Because what I taught you a couple of units ago was, okay, that's work. I'm going to be more specific. This area is the work done in moving an object from location A to location B. And since work is measured in joules, it's also telling me how much energy was required to move this object from location A to location B. Got the argument okay, Mal? We're going to now extend this to gravity. I'm going to put gravitational force Fg. So on the y-axis, can you put Fg in newtons? On the x-axis, instead of d, it's going to be r. What would this graph look like? Don't write this down, just look up. Who's in Pre-Calc 12 this semester? Okay. Fg equals big G, don't write this down, big M, little m over r squared. You know what? Really, the force of gravity is proportional to 1 over r squared. Just to give you a better math memory, instead of an r, I'm going to put an x there. What's the graph of x squared look like? You flog this to death in grade 11. It starts with letter, yeah, Sarah? Parabola. This is the reciprocal of a parabola, which I think you, in Pre-Calc 12 this semester, looked at reciprocal graphs, and you said, okay, where they're getting smaller, the reciprocal gets bigger. Where the reciprocal gets bigger, where it's zero, there's an asymptote. So this is the reciprocal of a parabola, so it's going to look kinda, you can all draw this like that. where as you get close to zero, it shoots off to infinity, and as you get further away from zero, you get smaller and smaller. Now, Quinn, does that make a little bit of sense? As you go further from the planet, does gravity get weaker? Okay, so at least it ties in with what we know. And yeah, it's probably not linear because it's an r squared on the bottom, not just something clean. All right. So consider, let's redraw that graph. Let's put an FG in newtons, an R, and let's do that little curve. But we're going to do the same trick as we did with our very, very first graph. I'm going to put a point right there, but instead of calling it A, I'm going to call it R Earth. That's where the surface of the Earth is. And instead of point B, I'll put a point here. I'll call it R Orb, short for orbit. This area is the work done in lifting a satellite from surface of Earth to orbit. Who here is signed up for calculus next semester? Okay. One of the things you'll learn near the very end of calculus, one of the things you can do with calculus is, don't write this down, find the area underneath curves. Because we don't have a formula for that. You actually need to derive it and do an equation method. And so if this was a calculus class, I would now say, hey, let's find a formula for the area, and that would give us our brand new cosmic potential energy equation. Are any of you in calculus right now? No. Okay. I'm going to have to do some shady math here, but it's going to get us to the right place. Are you in calculus? Was there someone in calculus over there? No? Okay. This is technically sloppy math, but it's going to get us to the right location. So I'm going to say, since work equals force times distance, we can say work equals gravitational force times R. That's force times distance. We can say work equals big G, big M, little m over R squared, there's gravitational force, times R. Is there an R on the top? Is there an R on the bottom? There's an R squared. You know what? One of the R's cancels. And so we end up with this. Potential energy, I'm not going to call it work anymore. I'm going to say this is the potential energy in lifting, like mgh, but this is cosmic mgh, is big G, big M, little m over R. Except, and here's where it's going to get a bit weird, so everyone look up for a second. It's negative. Why is it negative? It's negative because when you do the calculus, you do end up with a negative in front of it, and that's the best explanation. But are any of you in calculus? No. Okay. First of all, let's write our equation. This is cosmic potential energy. It's negative big G, big M, little m over R. Not R squared, R. And I think I gave you that on your formula sheet, I hope. Did I not? Nick, yes? Okay. Why negative? Calculus. But that doesn't work. Okay. When we set up this idea, we had to decide Where is zero energy going to be? Now, when we did roller coasters and things, it made sense, Lena, to let zero energy be the Earth's surface because we were doing things on the Earth's surface. But now we're going cosmic and we want to include other planets. Letting zero be the Earth's surface would be very egotistic and also just not mathematically convenient. So we said this. How about zero is where there's no gravity? Where is there no gravity? Technically, the only place where there's no gravity is when you're out at the edge of the universe. When R approaches infinity. When you're so far away, gravity's getting weaker and weaker and weaker and weaker and weaker and weaker. Do you know when there's no gravity? When you're all the way out at the edge of the universe. So I'm going to stand up. Sorry for those of you on YouTube. So I'd like you to imagine that the Earth is, where's my Earth analog? I'll use this. Here's the Earth. I'm going to put it right here. As I move further away, gravity gets weaker and weaker and weaker and weaker. And let's suppose way out here, we're out at infinity. How much energy does it have? We're going to define this as zero. And the reason we know it has no potential energy is because there's no gravity, if I let it go, it won't fall. That's going to be our definition of zero. Zero potential energy is if you let it go, it won't fall. If I'm closer and I let it go, there's gravity and it will start to fall. Because it started to move, because it started to fall, it's gaining kinetic energy. That energy had to come from somewhere. It must have had some potential energy. So we have a phrase for this. We say relative to zero at infinity. This is in our notes, and we're going to write it out in just a second. We say that relative to zero out at infinity, this is where we have zero potential energy. So how much energy do I have here? Zero. Again, how much energy do I have out at infinity? Everybody? Okay. How do I get to infinity? Well, to get to infinity, I would have to do work. I would have to add energy by burning rocket fuel to this system. I do have to add energy to get to infinity. How can I add energy but end up at zero? I must be starting out negative. Closer to Earth, you have negative potential energy. So you ready? Why negative? Out at infinity, at the edge of the universe, an object would have zero potential energy because it's not being affected by any gravitational field. It can't fall. If you let it go, it'll just stay there. If our height is less than infinity, we have less potential energy. What's less energy than zero? And so we use the phrase to hint that we want you to use cosmic potential energy. Sometimes you'll see them say relative to zero at infinity. Your hint is going to be, hey, if we're going cosmic, you want to use it. You might also see this phrase abbreviated relative to zero at infinity. In my homework, sometimes I'll say RTZAI, and that's my way of saying, don't you dare use MGH. Okay. Example 1. A mass is released from a height of 6,300 kilometers. Okay, Duick. Nice try. (6,300 kilometers) times by 1,000. 6.3 times 10 to the 1, 2, 3, 4, 5, 6. Meters. Ooh, and then what word did I underline right next to it? That's not a radius, so I'm not going to use that. I'll have to adjust it. How fast will it be going when it hits the ground if we ignore air resistance? Okay. Well, Finley, what's this question asking me to find? Did it say find the velocity? Say no. How fast, which suggests maybe I can use a scalar approach. Is there a change in speed? Is there a change in height? Is there a yucky, curvy gravitational field? This is going to be a job for conservation of energy. Okay? Now, right now, that seems very strange to you. We'll practice a bunch of these, and you'll realize Yeah, conservation of energy. So it's going to look like this. KE initial plus PE initial equals KE final plus PE final. Which one of these is the energy of motion? KE. Are we ever at rest? Well, released from a height, I think I can say that. What about potential energy? Are we ever zero? And this is the weird part. We're not zero on the Earth. Where are we zero? All the way out at, I'm looking for a word that starts with letter I. Infinity. I don't think we're at infinity anywhere in this question, so potential energy is not zero anywhere. But we are cosmic. We're above the Earth, so I'm not going to use MGH. I'm going to use my new cosmic potential energy, which is going to look like this. Negative big G, big M, little m over R initial equals a half little m V final squared plus negative big G, big M, little m all over R final. So this is still conservation of energy, but we're just using our new cosmic potential energy equation. Will a massive asteroid and a small asteroid hit the Earth at the same speed? How do you know? Little m's cancel. Now, will they do the same damage? No. Okay? So don't think that the m's cancel in terms of damage, but they certainly do cancel in terms of speed. This is around where my love for getting stuff by itself ends. Here's what I'm going to do. I'm going to plus this mess to that side, and then I'm going to turn that whole mess into a single number. Then I'm going to get the V by itself. I'm not going to try and get the V by itself algebraically. When you have multiple complicated fractions, trying to get stuff by itself just really isn't clean or worth it. So I'm going to do this. Negative big G, big M, little m over R initial, and then it's plus because this was negative. Big G, big M. Oh, no, wait a minute, Mr. Dewick, the m's canceled. Big G, big M over R final. Don't need to write the little m's. That equals 0.5 V squared. Put your calculator down. Fiddly. Don't go to your calculator yet. I'm going to try and show you. I've thought about this a long time, and I'm going to try and show you a method that's the least amount of typing and the least amount of error. I used to have kids type the whole thing in because that's my love, and they always made typos. It drove me cray-cray. So be patient for a second. First of all, negative. Oh. What's big G? Okay, the fact that we know it, I said last day, I won't make you write out 6.67 times 10 to the negative 11. If you want to, you can abbreviate that. What's big M? It's the mass of the Earth, which was what? So I'm just going to write mass Earth, and I'll trust that you can find that on your formula sheet. What's my initial radius? Well, if we kind of imagine what's going on here, here's the Earth. This right here is the 6.3 times 10 to the 6th meters. It's an altitude. I want that, a radius. How can I figure out the total distance from the center of the Earth if you give me the distance above the surface of the Earth? Sarah? Loud and proud. Okay, so our initial is going to be 6.3, stay in the same color, Mr. Dewick, 6.3 times 10 to the 6th plus, what's the radius of the Earth? Okay. All right, that's the first term. Plus, same thing times same thing. I'm actually going to use what we call ditto marks. Yes, because it's going to be a lot of writing. Big G, big M. All over. What's the final radius? I think the final radius is the surface of the Earth, which is just 6.38 times 10 to the 6th. That equals 0.5 v squared. And I haven't left anywhere near enough room. I'm feeling guilty right now, but maybe you'll have to write small. So get your calculators out. Here's my advice. We're not going to type both of these. Type the first one in very, very carefully. If you have your fancy schmancy fraction button, use that. Otherwise, it's going to be negative 6.67, scientific notation button, negative 11 times 5.98, scientific notation button, 24, divided by, is there more than one thing on the bottom? For me, I have to put brackets around the bottom. 6.3, scientific notation 6, plus 6.38, scientific notation 6. Close off the bottom. And if you hit enter, once you've typed that in, Kara, all of you are typing that in, you should have negative 3145630.9.15. Get that on your calculator, please. If you didn't get that on your calculator, now is your chance to ask. Do you notice how the second fraction is almost identical to the first fraction? I'm going to use that to my advantage because this is why I yelled at you about getting a good calculator way back in Physics 11. Got to get that okay? Negative 3.1. Okay. I'm going to write it to a few sig figs. I'm going to go negative 3.14. I'm probably going to carry it to 5 sig figs. Negative 3.1456 times 10 to the 1, 2, 3, 4, 5, 6, 7. So I'm running out of room. I'm going to have to go over here. Negative 3.1456 times 10 to the 7th. And then there's a plus sign. The second fraction, all I'm going to do is backspace on my calculator. So figure out how to bring back the previous line. I hope you've all figured out how to do that on your calculator by now. And it seems to me all I need to do is this. Delete, 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 delete. Oh, and delete the negative. Delete. Is that right, Lily? Okay, so I think on the TIs, it's second function equals brings back the previous line, or maybe up arrow, I can't remember. Yeah? So the second fraction, as long as I type in the first fraction very, very, very carefully, the odds are I'm not going to make a typo on the second fraction, Zaina. I get positive 625,18181.82. Yep. Okay. Pause. So for the second fraction, I get 625,1. I'm going to go 6.2518, 5 sig figs, times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay. 6.2518 times 10 to the 7th. That equals 0.5 v squared. So now what? Well, now I'm actually going to add those two together. Wonderfully, I have the second number still stored on my calculator. So I'm going to go negative 3.1456 scientific notation button 7 plus, haha, answer button. Right, Nick? If you do that, you should have 59372581 and change. So I get Wrecked it totally. Rats. Now I can't use my answer button. Yes, I can. Okay, there it is. And so I'm going to go negative 3.1456, thank you, Emilio, times 10 to the 7th plus answer button. Let's try that again. Do you have 3106218.82? Okay. That's what equals 0.5 v squared. I'm going to write that. Except I don't want to write this whole thing out. I'll start on my calculator. I'll go 3.1062 times 10 to the 1, 2, 3, 4, 5, 6, 7. 3.1062. Are you still with me? You can't quit. So the next one, I'll be looking for each answer from you. How would I get the V by itself? Divide what? 0.5 and then? Okay. Divide by 0.5 equals square root answer button. And we're going to hit the ground, and that's about right. Asteroid impacts are moving pretty fast. You're going to get something in the thousands or maybe even in the tens of thousands. So I get 7,880. Now I'll finally go to 3 sig figs. V final equals 7,880 meters per second. Whew, that's a lot of typing. It's rocket science. What were you expecting? 2 lines and you're done? So that's an example of using conservation of energy. Now, how did I know to use conservation of energy? Finley, what did they ask me to find? Speed. The other question I'll throw at you is, example 2. Lena, what's example 2 asking me to find? How much what? Work. Okay? These are the 2 main types of questions involving cosmic potential energy. I might ask you to find a speed or a height. That's going to be conservation of energy. Or I'll ask you how much what? How much what? Look up. Don't write this down. Why can't I go force times distance? Why can't I go like that? Gravity's changing. I could go the area under a force versus distance graph, but we saw it's going to be a curve, and you need calculus to do that. So I have to use my third definition of work, the work energy theorem. This is the one that has the change ins in it. Work equals change in potential plus change in kinetic. Alex, what word did I underline? I did that on purpose. So example 2, all we're asking is how much work, how much energy to lift the satellite to the right height. We're not giving it any kinetic energy because do you see the word stable orbit in this question at all? I'll compare that with the next example 2, which we're going to call example 3 once we get there. We're going to put it in an orbital radius with an orbital speed. So let's go back to this one here. What's it want us to find, Lena? How much what? Okay, because we're lifting, you can assume our speed is 0, which means there's no change in kinetic. It's starting at rest before we fire the rocket, and it's ending at rest once it's up there. Somehow an invisible leprechaun is just holding it there. Honestly, what's going to happen is it's going to come crashing back down to the Earth. We've launched it straight up. It's slowing. And it's going to come and hit the Earth, but we're not asking how fast it's going to hit the Earth. How do we know we're not going to find out how fast? Because they said how much work. What's change in anything? Okay. PE final minus PE initial. Oh, this is going to be easy. It's going to be don't write this down. H final minus MGH. Why can't I go MGH final minus MGH initial? Little g is changing. We've got to go cosmic. it's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Now, Wolf, you might be saying, Mr. Dewick, we're going to get negative work. That's going to say that we're gaining energy. We won't. We will end up with a positive answer if we do this right, because it will take us supplying rocket fuel. By the way, Wolf, what's a minus minus the same as? On the next line, we'll write that as a plus. Okay. Well, here we go. Negative. Do I know big G? 6.67, so I'm just going to write big G. Do I know big M? Mass of the Earth. Do they cancel, Keegan? There's an M there. I heard Keegan say masses cancel. There's an M there. Is there an M in work? And by the way, they shouldn't cancel. It should take more rocket fuel to put something larger up there. Like if I think about it, Keegan, it makes sense. Putting something larger up there should take more rocket fuel. The M's here should not cancel. So what's little m? Okay, and this is why NASA will spend hundreds of thousands of dollars making their satellites lighter. They'll spend the money to make it lighter. In the long run, you'll save on the rocket fuel. Divided by... what's our final radius? Well, here's a word all of us should have underlined. Height. That's how high we are above the Earth. So I guess if I want to turn that into a radius, it's going to be 1.2 times 10 to the 7th plus radius of the Earth. What is the radius of the Earth? Everybody, what's the radius of the Earth? Everybody, including Zaina, what's the radius of the Earth? Still everybody, including Zaina, because right now Zaina doesn't know where it is on her formula sheet. I'll let you abbreviate the radius of the Earth with RE if I know that all of you know what the radius of the Earth is. So what's the radius of the Earth? Everybody. You found it? Okay. Then there's a minus minus, which is a plus. The same number times the same number times the same number. We call those ditto marks because you're just repeating the same thing as you did before. And that's my way of saying you're going to just backspace and edit on your calculator. What's the final radius? Maddie, you're right. Yep. Again, what we're going to do is we're going to crunch this to maybe 5 sig figs, write it down, backspace, edit, tweak what we need to, probably delete the negative and delete the 1.2 times 10 to the 7th, hit equals, and then we've got that second number in front of us and store it on a calculator. This is the least amount of typing to do these. I played around with this and tried various different permutations. This is about how it's going to work. So, get your calculators out, everybody. Nick, what's the first thing I'm going to type? Good. Then 6.67 times 10 to the negative 11. Oop, I missed the negative. That would have been a problem. Times mass of the Earth, 5.98, scientific notation 24. Times 1200 divided by, I have to put the bottom in brackets, 1.2 times 10 to the 7th plus 6.38 times 10 to the 6th. Nick, did you get negative 2 points? Oh, now it's giving us an answer in scientific notation. Negative 2.6041 times 10 to the 10th? I'll carry 5 sig. Basically, I carry 4 or 5 sig figs to guarantee that when I combine everything at the end, I'm good to 3 sig figs. So negative 2.614, sorry, negative 2.6041. Write that one down. And then drop the plus sign down. that okay, Reed? Typo, yeah. And that's going to be by far the most common error on these. You are, unfortunately, and I haven't figured out a way around it, going to get frustrated when you've done 15 lines of work and your answer doesn't match mine. That's because you made a typo on line 2. Sorry. Type really meticulously. Now what? Bring back the previous line. I know if I go up arrow a few times, that takes me to the beginning. That's how I get rid of the negative. That's like hitting home on your computer. And then delete, 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 delete. $7.5022 times 10 to the 10th. Lena, what are they asking me to find? Oh, I think it's just going to be these two combined. So, negative 2.6041 scientific notation button 10 plus, oh, I can just go answer button. That's a bonus. How many joules of rocket fuel will it take to lift this satellite up? 4.898 times. So, little rule of thumb. If I'm giving you good questions, which I will try to, you'll find typically the amount of rocket fuel will be in the 10 to the 9th, 10 to the 10th, or 10 to the 11th range for joules. If you're around the moon, it'll be a bit less because the moon has weaker gravity. 4.90 if I round off to 3 sig figs properly. Did you get that okay? Okay. Is that a fairly big number? Yeah. It's really, really expensive. It takes a lot of rocket fuel for us to put stuff. Oh, this isn't even in orbit. This is just getting it to the right height. To keep it in orbit, what do I need to do? I need to also give it some kinetic energy. So if I'm going to put it into a stable orbit, I'm not going to cross that out. In fact, I wrote here, since this satellite has no kinetic energy, basically all we've done, if this tennis ball is the satellite, is we figured out how much work to get it up there, but it's going to come crashing back down right away, unless we give it the right sideways energy. To lift an object, we only need to give it. So when you're doing work, you can cross out the change in kinetic. Change in kinetic. But to put an object in a stable orbit, we need to give it potential energy and I like example, cross out example 2, make it example 3. I like example, cross out example 2, make it example 3. I like example 3. This is almost the most amount of writing you'll do for a single question. It'll be about a full page. Nick's shaking his head. It's rocket science, Nick. What were you expecting? 2 lines and you're done? Please. Okay. Reed, what's this question asking me to find? So don't be going kinetic inertial, don't be using conservation of energy. We're going to have to use our complicated work energy theorem. Work equals the change in potential plus the change in kinetic. Everybody underline the word orbit. Unfortunately, we can't cross out any of these change-ins because there's kinetic energy and potential. But we can make our life easier. I'm going to do these one at a time. Keegan, what do you want to find first? The change in potential or the change in kinetic? I don't care. Pick. Change in? Okay. The change in potential is, what's change in anything? Final minus initial, which again is really weirdly tricky to say for some reason. Minus initial, I've heard that all the time. Can I use MGH? No, we're cosmic, so it's going to be negative big G, big M, little m over R, there's my final, minus negative big G, big M, little m over R, there's my initial. In fact, it's going to be really similar to what we did. Oh, except They didn't give me the altitude. They gave me the orbital radius, so I won't need to add the radius of the Earth to this one. So you can also underline that word as well. That's a good trigger word. All righty. Here we go. Negative, big G, big M. What's little m? 925. All over. Our final is just 2.6 times 10 to the 7th, because it's a radius they gave me. If they had said altitude of 2.6 times 10 to the 7th, or height of 2.6 times 10 to the 7th, well, that's above the Earth's surface. I got to include the radius of the Earth. Here, they already included the radius of the Earth, so bonus. Oh, what's a minus minus the same as? Plus. Same thing times same thing times same thing, all over radius of the Earth. Which is what, Zaina? Okay, you know where it is. Good. I'm going to do the first term. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 925 divided by 2.6 scientific notation button 7. If you've typed that correctly, let me look for typos, you should get negative 1.419 times 10 to the 10th. And I think that 9 is a good place to round off to, because next to it is a 0. Am I right or am I wrong? Yes? Okay. If you're all getting different answers, let me know, because there's a good chance I'll make a typo. This is a pretty complicated typing stuff. Negative 1.419 times 10 to the 10th plus, and then I'm just going to backspace. I'm going to delete the negative, and I'm going to replace the 2.6 times 10 to the 7th with 6.38 times 10 to the 6th. Whoop, wrong button. Really? There we go. And I get positive 5.7829 times 10 to the 10th. Whew. Okay. Let's get an answer for the change in potential energy. It's going to be negative 1.419, scientific notation button 10, plus answer button. How much rocket fuel just to get it to the right radius? Apparently 4.3639 times 10 to the 10th. Joules. I often put a box around this because I know I'm going to be looking for it later. Are we done? What else do we need to find? The change in kinetic energy. So, okay. Change in kinetic energy. Boys and girls, what's change in anything? Now, kinetic energy, that equation hasn't changed. It's going to be a half mv final squared minus a half mv initial squared. We are going to assume that v initial is 0. We're starting at rest. In real life, are we? How? Read. In real life, we launch in the direction that the Earth is spinning. Where is the Earth spinning the fastest? Along the... Where is Earth spinning the fastest? Along the equator. The smartest place to launch would be from the equator. Now, the U.S., the reason they launch from Florida is because that's the furthest south, aside from Hawaii, which doesn't have the infrastructure, that they can launch. And they launch over the Atlantic for two reasons. Number one, they're taking advantage of the Earth's spin. Number two, if they have to abort, they can blow the rocket up over the ocean and do less damage. Russia did not have that advantage. Russia, one of their challenges in the space program, because they're further north, they didn't have as much of the Earth's spin to use. And so that's why even to this day, Russian rockets are just workhorses. They had to just build these mother big rockets in order to overcome the fact that they don't have the advantage. Where would there be no advantage from the Earth's rotation? So we're going to imagine that either Superman or Santa Claus has a rocketry program. So you can imagine we're either launching from Superman's Fortress of Solitude or from Santa's workshop. For the rest of this unit, we're going to ignore the advantage that you get from the rotation of the Earth. So you can put equals 0, and then you can make a mental note, either Superman's Fortress of Solitude or Santa's workshop. Okay? By the way, that's also one of the reasons Elon Musk is trying to learn how to launch from ships, because his argument is if we can launch from a ship, you can put your ship in the ocean right on the equator. Save yourself a lot of rocket fuel. Do I know little m? Do I know orbital speed? Then it's just plug and chug. 0.5 times 925. What was the orbital speed? 3917. Don't forget the squared. Usually you'll find your orbital speed is 1 power of 10 smaller than the potential energy, the work. In other words, I'm going to guess instead of a 10 to the 10th, you might get a 10 to the 9th. It might be a 10 to the 10th, but I'll bet you it's a 10 to the 9th. (7.0961) times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Did your calculators give you the answer in scientific notation? Yeah, okay. So 7.0961 times 10 to the 9th. Excuse me. He already has, thanks. Are we done? No! This is rocket science, baby. Jan, what did this question want me to find at the very beginning? How much? Okay, and what did we say work was equal to? First line, what did we write? Oh, which is 4.3639 times 10 to the 10th plus, what did we say that work was equal to? Change of potential plus, which is 7.0961 times 10 to the 9th. Whew! No pun intended, this is a lot of work. Mr. Dewick, why would you type out 7.0961? Use your answer button, Mr. Dewick. Check for typos. That looks good. Did you all get 5.07 times 10 to the 10th joules? That's how much work to put this satellite in orbit. Whew.